Hey everyone, and welcome. Today, we're diving into a phenomenon that is literally all around us, but you probably don't even notice it. It's a kind of secret frequency, one that can make bridges sway, shatter glass, and even tune your radio. We're talking about resonance, and we're going to see just how much it shapes our world.
So, to kick things off, let me ask you a question. What on earth could a radio tuner possibly have in common with a kid on a playground swing? I know, it sounds like a weird setup for a joke, but the answer actually unlocks one of the most fundamental principles in all of physics.
And that powerful principle is resonance. That's the secret link between the two. See, resonance is all about timing. It's about applying just the right amount of energy at exactly the right moment to get a massive, almost unbelievable result.
Visit youtube.com/avidsystem and don't forget to subscribe.
To really wrap our heads around this, we have to start with that idea of the perfect push. We're going to break this whole thing down using probably the best, most intuitive example you can think of.
Just picture pushing someone on a swing. You know you can't just shove it whenever you want, right? It just doesn't work. You have to get the timing just right. You give it a small, gentle push, right as the swing hits its highest point and is about to come back. That little push adds energy. That perfect timing, well, that is its natural frequency. It's resonant frequency. And here's the magic. With a bunch of those small, perfectly timed pushes, you can get that swing going crazy high. A huge effect from a tiny, well-timed effort. That, my friends, is resonance in a nutshell.
Okay, so we've got the physical example down cold. Now, let's take that exact same idea and swap out the playground for a circuit board. It's time to meet the electronic version of our swing. And here it is, the star of our show, the parallel RLC circuit. Now I know, it might look a little complicated, but trust me, it's just our swing belt with electronic parts. It has three main components, and each one of them has its own little personality.
First up, we've got the resistor, or R. You can think of this guy as the friction on the swing's chains. It's our steady resistor. Its job is simple. It provides a constant, unchanging opposition to the flow of electricity. It honestly doesn't care what the frequency is, its opposition is always the same.
Next, let's meet the inductor, L. I like to call this one the change hater. Inductors are basically coils of wire, and they absolutely despise quick changes in current. So, what happens? As the frequency of the current starts to go up, the inductor's opposition, we call that reactance, goes up too. It fights back harder and harder against those higher frequencies.
And finally, we have the capacitor, C. Now this component is the complete opposite of the inductor. It's the change lever. It loves to store and release energy, and it has zero problems with high-frequency currents. In fact, the higher the frequency, the lower its opposition gets. It basically just lets those high frequencies zip right on through.
So, we've met our cast of characters, the steady resistor, the change-hating inductor, and the change-loving capacitor. Now it's time for the main event. Let's talk about the canceling act. This is what happens at one very, very special frequency where our two opposites have a little showdown.
This special frequency has a name, of course. It's the resonant frequency, or FR. And it is the one, single, unique frequency where the opposition from our change-hating inductor becomes perfectly, exactly equal to the opposition from our change-loving capacitor. It's a perfect mathematical standoff.
So what does that standoff actually do to the current? Well, because their oppositions are identical, the amount of current flowing through the inductor and the capacitor is also identical. But, and this is the whole key, they are 180 degrees out of phase. That just means that at any given moment, they're flowing in completely opposite directions. When one zigs, the other zags. And what happens when you have two forces that are perfectly equal, but moving in completely opposite directions? You got it. They effectively just cancel each other out. As far as the power source feeding this circuit is concerned, it's like those two currents don't even exist.
This whole canceling act leads to a result that is, well, pretty surprising and incredibly powerful. We call it the impedance peak. So what? Who cares if these two internal currents just vanish from the power source's point of view? What is the big deal here?
This is where the magic happens, because those two reactive currents cancel out. The only thing left for the power source to deal with is our good old steady resistor. And that means the circuit's total opposition to current, what we call its impedance, just goes through the roof. It hits its absolute maximum. The circuit basically throws up a giant stop sign, making it incredibly hard for the source to push any current through at this one specific frequency.
And this table here just lays it all out perfectly. If you're at a frequency below resonance, impedance is low, so current is high. If you go above resonance, same thing, low impedance, high current. But right at that resonant sweet spot, bam! Impedance is at its maximum, which means the current coming from the supply drops to its absolute minimum.
And because it's so good at stopping or rejecting the current at that one specific frequency, we have a cool name for it. This setup is often called a rejector circuit. Pretty fitting, right?
Okay, let's bring it all back home. We went from a swing to a circuit, and now we're going back to that radio tuner from the beginning. Let's see how all this theory actually lets you tune into your favorite song.
It's actually genius in its simplicity. So your radio's antenna is getting blasted by waves from tons of different stations, all on different frequencies. When you turn that dial, what you're really doing is changing the value of the capacitor or the inductor inside that RLC circuit. And by doing that, you're changing the circuit's resonant frequency. When you dial it in just right so that the resonant frequency matches, let's say, 101.1 FM, that one station's frequency suddenly faces a giant wall of impedance. The circuit rejects it, which actually pushes that one signal down a different path to get amplified, while all the other frequencies just pass right by. And just like that, you're listening to your station.
So let's do a quick recap. What are the key things to remember? 1. Resonance happens at one single special frequency. 2. In a parallel RLC circuit like the one we saw, this means you get maximum impedance. 3. That also means you get minimum current from the source. And 4. This amazing rejector effect is what makes things like radio tuners and all sorts of electronic filters possible. It's pretty wild when you think about it. If one specific frequency can have such a massive effect inside a tiny electronic circuit, it makes you wonder, what other hidden resonances are out there shaping our world? From the way musical instruments are designed to how massive bridges are built, this secret frequency is hiding in plain sight, quietly influencing everything. The real question is, where are you going to see it next?
Thanks for watching.